Stan Gibilisco here. I'd like to talk a little bit about a full wave loop antenna. This is a ham radio antenna. I am a ham radio operator. Call sign W1 GV Whiskey 1. Good vibrations at your service. Here is a typical full wave loop antenna. Now imagine that you are standing somewhere looking right down the axis of this loop antenna. It's a square loop. Each side measures 1/4 of a wavelength, so the circumference is a full wavelength. The feed line goes to the center of the horizontal section on the bottom of the square, and I say bottom because this square is oriented in a vertical plane, so the axis might run, say, north and south, in which case in this view you might be looking directly south, or it might run east and west, and then in this case you might be looking directly east. So that is a typical antenna for amateur radio use, particularly on the frequency bands ranging from approximately 14 megahertz to maybe 144 megahertz, 20 meters up to 2 meters. So you can make them larger. You can make them for 7 megahertz, in which case each quarter wavelength side would be about 33 feet or 10 meters long. In the case of a 20 meter antenna, the circumference would be about 20 meters. So each side here would be about 16 or 16 and a half feet long. Actually, when you have a full wavelength loop like this, you should make the antenna pretty close to a full wavelength in free space. In fact, the formula, as I recall, the circumference C in feet is 1,000 divided by the frequency in megahertz. That is an approximate formula. Let's just make a calculation here. Bring up our handy dandy calculator and divide 1,000 by 14. 71 and a half feet. So each side of the antenna, or each leg of the square, would be approximately almost 18 feet long, 17.8 feet long. I'm not exactly sure why this formula is the way that it is. You would think that if you were taking it into account like a dipole with a velocity factor, then you would have a formula something more like on the order of 930 or 940 over F. But that is the formula as I recall it. But in any case, you would want to cut it for the lowest standing wave ratio on a transmission line. When you do this, at this point right here, you get a purely resistive impedance, and we can call that R, equals approximately 100 ohms. So if this is 50 ohm coaxial cable here, you're going to have a 2-to-1 standing wave ratio. If it's 300 ohm window line, you'll have a 3-to-1 standing wave ratio. In either case, though, that isn't too bad of a standing wave ratio, and it's not really enough to worry about. Even 100 ohms, 2-to-1, most radios will accept a 2-to-1 standing wave ratio. But here's the way that this antenna works, and it's really rather interesting. You have a current loop right here at the feed point. So you have, let's say, a maximum current flowing in this direction counterclockwise around the loop. It goes to the right in this view. Let's just say counterclockwise at some instant. Your peak current is counterclockwise, and so it points to the right. You get halfway around the loop, you're half wavelength away from here, so the current will again reach a loop or a maximum, but it will be flowing in the opposite sense around the loop, that is to say clockwise. But because the wire is going around in the other direction, clockwise turns out to be once again towards the right. So you have two current loops spaced a quarter of a wavelength apart from each other, stacked one on top of each other. In effect, you have a sort of phased array, a sort of a mutant version of what they call a broadside array. When you phase multiple current loops like that, and they will appear in phase anywhere along the axis of the loop, you actually get a slight gain over a dipole. And again, I don't recall exactly what that gain is. It's not much. It might be 1 or 2 decibels with respect to a dipole, that is to say 1 or 2 dBd. But you actually get a little bit of gain along the axis of the loop with compared to a plain half-wave dipole. The maximum radiation and response in a loop like this is right along the axis. So if you're looking at the loop broadside like this, you are going to be right square in a radiation maximum. The radiation minima are off to the sides like this, but they're not zero. There's no null in a loop like this. The main radiation lobes go along the axis of a full wave loop. Now this type of a loop can work quite well as an alternative to a half-wave dipole if you have the space. And interestingly, you could just rotate this whole thing 90 degrees counterclockwise. Whoops. I don't want to write that in bold like that. You could rotate it 90 degrees counterclockwise, feed it over here, end up with vertical polarization rather than horizontal polarization as you see here. That way you can get away with placing the loop much closer to the surface of the Earth. So these are just some notions, some design ideas for you, some theoretical characteristics of a full wave loop antenna. You can also make parasitic arrays out of these things. You can add a director and a reflector like you would do with a Yagi, and in that case they call the antenna a quad. In fact, if you have a 2-element quad with the elements spaced about a quarter of a wavelength apart, it's almost like you have a cube, and so they sometimes call it a cubical quad antenna. Stan Gibilisco signing off, saying 73 for now. So long.